Hello Year 7, it's Miss Redmond again with your fourth lesson on the forces topic. If you haven't got one already, please pause the video and go and get a pen so that you can make notes and do the little tasks that I'm going to give you as we go through. So this lesson is called What is Gravity, and it's all about non-contact forces. Here is your learning journey. Feel free to pause the video now and write those things down. And your DNA is what jobs might need to use knowledge of gravity. So write down your ideas, and if you want to, you can check with your teacher when you're back in school. All right, here are some examples of non-contact forces. So in a non-contact force, the two objects don't have to be touching. So the ones you need to know about are magnetic force. So the magnet doesn't need to touch all of these iron filings in order to have an effect on them. So you can see that it's attracted lots of iron filings to it, and they're stuck on the ends and they're stuck on the magnet, but it's also moved these ones that are still on the paper. So it's not in contact with those iron filings, and yet they can feel the force. Next example is electrostatic force. Now, I want to believe that the cat jumped into the box of packing materials on its own and got them stuck to them, and somebody didn't do that to the cat, because that would be very cruel. You can see how upset the cat is. That's quite funny. And the other force that you need to know about is gravity, or gravitational force. So this is Jessica Meir, who you will see a bit more of in the space topic, and she is up doing a spacewalk on the International Space Station, and she is actually taking a selfie in the reflection of the solar panel. So this is the camera, and these lines are the lines on the solar panels. I just thought that photo was so cool. All right, so here are some links to some YouTube videos explaining in a bit more detail about magnetic force and electrostatic force, these two non-contact forces. So this one is a really cool video about an artist who uses magnets in his work, and this one explains really nicely what electrostatic force actually is. So I encourage you to go away and watch those videos at some point. Okay, you need to know what a field is. A field is the space around an object where the force can be felt. So magnets have a magnetic field. This is a diagram of that. So you've got a bar magnet, and these lines are showing you the field of this bar magnet. So the area around the magnet is called the field, the magnetic field, and these lines are showing you a diagrammatic form of that. So you can see that the magnetic field lines go from north to south. So the arrows are going from north to south, or they're going into the South Pole and they're going out of the North Pole. Okay, objects with a static charge have an electrostatic field. That's these two diagrams here. So you've got a positive charge and a negative charge attracting each other, and you've got two positive charges repelling each other. So like charges, the same charge, positive and positive, repels, and opposite charges, so positive and negative, attracts. Similar to the bar magnet, a north and a north will repel each other, a south and a south will repel each other, and a north and a south will attract. That kind of makes sense. If you look at the field lines, you can imagine if you were to bring a north pole in here, the field lines from that magnet would be pointing out, and the field lines here are pointing in towards that South Pole. So as soon as you bring that magnet into the magnetic field of this one, it's going to suck in, it's going to attract to that South Pole. So north and south attract, and then same poles repel. And all matter has a gravitational field. That's this diagram here. So this is slightly different to the other two, in that gravity always attracts stuff. but it's got to be pretty big. That's why we've got a diagram of the Earth. So all of these arrows are pointing in towards the Earth because it's showing you the gravitational field of the Earth pulling all matter in towards it. And the other thing you need to know about fields is that each of these gets weaker as you go further away, which kind of makes more sense, right? You feel gravity stronger when you're on the surface of the Earth than you do when you're up, like Jessica Meir, on the International Space Station in orbit, right? Or the further away from a magnet you are, the weaker the force that you can feel. I'm sure you've experienced that in everyday life when you're playing with magnets. You have to move them closer and closer, and then the closer you move them, the stronger you can feel the effect. Just for the sci-fi geeks, you may have heard gravity referred to as a gravity well. That's because gravity always pulls objects towards it. And this is a diagram showing you the idea of a gravity well of the Earth. Okay, you need to know about the difference between mass and weight. Mass is a measurement of how much stuff there is, and it doesn't change depending on where the object is. And it is measured in grams or kilograms. So in this lesson we're going to use kilograms, but you also need to be aware of grams. On the other hand, weight is the force of gravity pulling an object down, and it depends on how much mass there is and how strong gravity is. So it changes depending on where the object is. So if you take something to Jupiter where gravity is a lot stronger, it's going to have more weight, but its mass won't change because you haven't added anything or taken anything away. So weight, because it's a force, is measured in newtons. And here's a little diagram explaining that. So this person's weight on Earth is around 560 newtons, whereas on the Moon, because gravity is weaker, their weight is 90 newtons. However, the person's mass is always 56 kilograms. So the mass is 56 kilograms on the Moon and on the Earth, but the weight is 560 newtons on the Earth, where gravity is quite strong, and only 90 newtons on the Moon, where gravity is much weaker. So mass doesn't change depending on gravity. Weight does change depending on gravity, and weight is a force. You can calculate weight using this equation. Weight measured in newtons is equal to mass measured in kilograms times by the gravitational field strength, and the units for that are newtons per kilogram. So for example, on Earth the gravitational field strength is about 10 newtons per kilogram. You might see slightly different numbers like 9.8 newtons per kilogram. Use whatever number they give you in the question. If they don't give you a number, use 10. So my mass is about 70 kilograms. So to calculate my weight, I do 70 kilograms times by 10 newtons per kilogram, and my weight is 700 newtons. So in everyday speech, I would say that my weight is 70 kilograms, but scientifically that's incorrect. 70 kilograms is my mass, and my weight is 700 newtons. But if I were to go to the Moon, where the gravitational field strength is about 1/6 of the gravitational field strength on the Earth, I would weigh something different. So my mass would be the same, my mass would still be 70 kilograms, but to work out my new weight on the Moon, I would do 70 kilograms times by 1.6 newtons per kilogram, and that would be 112 newtons. Mini challenge for you. Can you tell me a quicker, easier way to do this part of the calculation? I'm not going to give you any more clues than that, but pause the video if you want to look at this slide and email me your answer. I'll tell you if you've got it right. But my maths would stay the same. Yeah, worth repeating that point. So here's your summary. A non-contact force is a force where the two objects don't have to be touching, for example, magnetic force, electrostatic force, and gravity or gravitational force. A field is the space around an object where the force can be felt, for example, magnetic field, electrostatic field, gravitational field. Each of these fields gets weaker as you go further away. Mass is a measurement of how much stuff there is, and it's measured in grams or kilograms. Weight is the force of gravity pulling an object down. It depends on how much mass and how strong gravity is, and it's measured in newtons because it's a force. The equation for working out weight is weight equals mass times the gravitational field strength. Thank you very much for listening, and I will speak to you next time.